Thank you, Pero, for this interesting presentation. My name is Christoph Petich. As speaker of the Rust Working Group, I will show you how to use this new programming language for enhancing quality in the classic platform. This presentation gives an overview of the recent activities inside the Rust Working Group. We have been working on the adaptive platform for a good 3 years. Now we want to leverage the benefits of the Rust programming language also for the classic platform. I will introduce the Rust programming language and its evolution in the adaptive platform over the past 3 years. Then I will present the current state in the classic platform and end with an overview of its use for different subsystems. In 2006, Rust started as a hobby project by the Mozilla employee Graydon Hoare. He combined the best of many languages from the 70s to the 90s. Since then, one goal was to enable embedded software with significant higher quality. At that time, the language used in academia and industry were at opposite ends of the spectrum. Academic functional programming languages like OCaml or Haskell focused on correctness guarantees, while industrial system programming languages like C and C++ focused on execution speed. Rust combines these divergent influences. It is originally named after a fungus over-engineered for survival. This fungus is well known since Roman times. It affects soybeans, coffee, grain, fruits, and many more. And as the quince in my garden gets infected year over year with rust, I get a regular reminder about Rust's durability. Rust, the programming language, is more strict on type correctness. But its unique benefit is checking ownership on a global scale. A function can only modify the object it exclusively owns. All shared objects are immutable. You can hand out temporary references to subprograms, and these are verified by the borrow checker to comply to this policy. This combination leads to thread safety and directly prevents use after free. Rust's module features distinguish multiple versions of the same library even within a single program. Because of its strict correctness checks, IDE autocompletion and AI-assisted coding become more productive. By default, Rust checks for buffer and integer overflows at runtime. Error propagation is convenient but explicit by using the question mark operator. We will see an example later. Functional programming and compiler-generated state machines reduce the amount of code which needs to be written for a task. In 2022, the Rust Working Group started to write adaptive applications in Rust. The interface to the stack, which is defined in the C++ language, needed a complex mapping to a binary interface defined in the C language. In 2023, we started a plan to standardize the C language binary interface, to then use it also for more programming languages. But this effort instead led to the proposal of another Mozilla-developed technology, which is WebAssembly interface types. WIT defines a high-level, language-neutral binary interface. And since version 0.3, which is to be published roughly around this event, it covers the full set of AutoSAR types: string, vector, result, future and even events. The code complexity for the C interface made the implementation of a stack in the Rust programming language impractical. But using VIT as an intermediate interface, this summer we created a first minimal Rust stack. It runs unmodified C++ and Rust applications which exchange events. Some prototypes demonstrate compiling adaptive or classic applications to WebAssembly components. This way, the same binary container works in browsers, POSIX, or microcontrollers. Sadly, we need pre-allocated buffers for publisher-subscriber and multi-threading features, and these are coming in future editions. But we already have early stages of prototypes. To use Rust for the classic platform, you need an RxML to code Rust code generator. It creates the application-specific parts of the runtime environment interface. We already have two independent implementations for this. Interfacing with the C interface is directly possible in Rust, but it requires code which can't be checked by the compiler for global correctness. To minimize effort, a minimal wrapper around this humanly verified code is created. This way, the Rust applications can avoid the unsafe keyword, which always indicates that manual review is necessary. The Rust programming language supports hierarchical namespaces, and this can shorten the long RTE function names, which are used by the application code. Optimization of a classic system is achieved by customization in RxML. To reach the full optimization potential, the Rust interface needs access to stack-specific internals. Thus, it requires vendor support. 2025 featured public statements by many stack vendors to support the Rust language for the classic platform. On the left, we see the code of a classic Rust application shown during this year's AutoSAR Open Conference in Bruges. This small application activates in LED when specific CAN messages arrive. First, it reads the current counter from an inter-runnable variable. Then it activates the LED, increments the counter, and finally sends the current value via CAN. On the right, you see the question mark operator directly returning from the process data function once the RTE call returns an error. The bottom example shows how pattern matching can be used to explicitly handle a specific error. This slide shows a mixture of Rust-specific idioms and the standardized classic platform function names. In our currently working group meetings, we discussed transforming these names into a more hierarchical and more object-oriented style. You see that a core partner of AutoSAR this year shared the results of an internal study about Rust for the classic platform. It shows a long-term benefit from using Rust for classic application development. The productivity increase and learning curve results align with findings at Google and Microsoft. As usual, new technologies need time to become more common practice across the industry, even if the long-term benefits are already visible. Gaps exist in MC/DC coverage measurement and quality assurance tools. but tool suppliers are already working on closing these gaps. While we initially concentrated on Rust for application development, other areas of the platform can also benefit. Complex device drivers expose a small surface to the outside world and are, as the name indicates, complex internally. So the extra effort at the interface to the C language, which is quite difficult, is outweighed by the increased quality inside the driver codebase. Similarly, Rust-based runtime environments code can be checked by the compiler for correctness. This safety net helps once the usually auto-generated code needs to be modified by hand. As Rust is also suitable for bare metal programming, its correctness can accelerate MCAL development. Rust developers are used to, once it compiles, it works correctly. Satisfying the compilation checks takes more effort, but then considerably less time is spent in the debugger. This benefit gains more weight once debugging becomes more difficult and the cost of undetected mistakes rise. Both these conditions are unique characteristics of embedded software. Thank you. As a quick reminder, all AutoSAR partners are invited to join working group meetings, which shape the software environment for years to come. Now I pass to Richard to present his